Yes, can hear you.
All right, great. Okay, nice to meet you all, even though I can't physically see you or interact with you. My name is Shaden. I'm a postdoctoral researcher here at UKZN. Just to give you some background about myself before we begin the formal session. As I said, I'm a postdoc researcher here. I've done my undergrad and my entire postgrad degrees here at UKZN. I specialize in majority of the aspects of hydrology, so strong focus in remote sensing, quite a bit of hydrological modeling, isotope hydrology, and what is the other one? Ecological or environmental interventions which can promote improve hydrological ecosystem services. So yeah, that's basically my background. Today, I have the pleasure of introducing you to the world of Google Earth Engine. If you're not familiar with it, it's an extremely powerful data processing platform specifically designed for working with satellite Earth observation data. But there are some additional features which permit you, you have the ability to actually upload your own data onto the platform and take advantage of all the processing capabilities that Earth Engine has. So we'll go through all of this, but before we begin actually working with the system, I just want to give you a brief overview of what Google Earth Engine entails. Let me just share my screen quickly. Can everyone still hear me clearly? Okay, so just someone give me an indication if you can still hear me clearly, if you can see my screen.
Yes, we can hear you.
Yeah. Perfect. Hi, Ms. Shetty. Okay, so.
I'm glad you're online. Welcome, everybody. I hope you're going to enjoy today's session.
Okay, so let me begin introducing you to Google Earth Engine and quickly giving you a brief overview of remote sensing and how this fits in with Google Earth Engine. Just to bring it or draw it to your attention, this is a very brief summary of Google Earth Engine and its capabilities and what it has been designed for. I think Ms. Chetty has uploaded some readings that I've provided where you can go and get a more comprehensive overview of what the system is all about. Okay, so to begin, we want to know, why do we want to use remote sensing data? So conventional in situ measurements and estimation procedures have been invaluable in improving our understanding of hydrometeorological variables. However, the application is limited by the spatial representativity of the estimates, the costs involved, and the labor requirements. A suitable and recommended alternative to in situ or conventional approaches of acquiring this data has been remote sensing. So when we speak about remote sensing, we can think of three different techniques which can be used. The one is satellite Earth observation, which will be the primary focus of our discussions in the session. You have manned aerial vehicles and unmanned aerial vehicles, which have special sensors which are integrated onto these platforms that enable them to capture data that are required for different purposes. So what is remote sensing? Remote sensing has a wide range of applications in environmental studies. It's the process of detecting and monitoring the physical characteristics of an area by measuring its reflected or emitted radiation. So when we speak about reflected or emitted radiation, you can use the sun as an example. So the sun emits its own radiation, and this radiation is then reflected off surfaces such as clouds, the land surface, the vegetation canopy, etc. And this reflected radiation can be measured by sensors. Alternatively, if a body has a certain amount of energy, for instance, the sun or the land surface, when it heats up, it can emit its own radiation, and this emitted radiation can also be measured. So sensors are designed to capture reflected or emitted radiation from a part or several parts of the electromagnetic spectrum. And this figure here just details the range of the electromagnetic spectrum. So majority of what we see and what a lot of sensors are designed to capture is in the visible region. And generally your sensors will capture data in the red, green, and blue. So these are your typical RGB sensors or cameras. You also get multispectral sensors, which capture a bit more information in the infrared and mid-infrared regions. And then thereafter, you have hyperspectral sensors, which capture in the thermal infrared and so on. So your sensors can be classified as active or passive. Active sensors emit their own energy pulse, which is then measured back by the system after it has been reflected by a specific surface, whereas passive sensors rely on energy emitted from other objects, so in all likelihood from the sun. Objects will return different amounts of energy in different bands of the electromagnetic spectrum, and this information then can help us derive certain key variables of interest. Okay, so the next component or the next part of the talk is looking at why is this important from a hydrometeorological perspective. So there's several advantages of utilizing remote sensing data to acquire hydrometeorological process information, and this has been well documented. Advancements in data capturing using remote sensing technologies, coupled with higher computing power, have facilitated the quantification of spatially explicit hydrometeorological data across space and time. And this has resulted in the provision of invaluable information for monitoring and preservation of environmental, hydrological, and agricultural systems. Okay, just making sure everyone is still following along. Please feel free to interject at any point and ask questions. If I am going too fast, just let me know and I'll slow it down a bit.
Yeah, it's okay, sir.
Okay, I'm going to take it. All good. All right, so the next important concept to understand is the resolution of the sensors that you're working with. So you generally get this trade-off between spatial, temporal, and spectral resolution. And this is probably more significant for the freely available data sets, but it can be applicable to the commercially available products as well. So just to expand on this concept of spatial, temporal, and spectral resolution, we have these images over here which are showing different features of interest that are being captured using different spatial resolution imagery. So up here at the top, if you can see where my cursor is, we have a very high resolution image capturing an area or a region of interest at 1 meter spatial resolution, the same area at 10, the same at 30, and the same at 250. So just looking at these different spatial resolutions, there's a certain amount of detail that can be extracted and interpreted from these images. So the first image at the top there, the very high resolution image, you can clearly see the different features that are being captured within the image. However, if we go to the coarser spatial resolution, it's hard to distinguish the spatial heterogeneity within the study area and what exactly is being represented or captured in this image. So from an environmental monitoring point of view, coarse spatial resolution imagery generally has a very high temporal resolution. So it's useful for routine monitoring due to this high temporal resolution. The challenge comes about with using this imagery for specific applications that the pixel sizes will generally exceed the area under observation. So if we had to look at this image at the bottom here, you can see there's this house that's denoted by these blue pixels or blue blocks, and there's a surrounding area which could be a yard or anything else. Could be a yard, could be vegetation, a road, etc. But the house and the other feature of interest is in red. So at this very fine spatial resolution, we're able to clearly distinguish between these two. And if you had to go to the pixel output display here at the bottom, you see at the very fine resolution, everything is captured as is. However, if you go to a far coarser resolution, you see that now some of the spatial heterogeneity within that specific region of interest is no longer being captured. So everything is now being classified as a house, whereas in reality, it's a house and something else. So when your pixel size generally exceeds the area of observation, you have the dominant land cover or dominant land use in that area contributing a majority to what information is captured within that pixel. So that can be a bit problematic. For example, if we had to think about the estimation of evapotranspiration, if you have a spatially heterogeneous environment where you've got natural grasses, agriculture, etc., and you want to know what is the ET of that area. So the ET for those different land use, land covers will significantly vary. And if you are using a very coarse spatial resolution image, it might only capture or adequately capture the ET of the dominant land cover. Say, for instance, it's grassland. And if grassland ET is substantially lower than the ET of your agricultural areas, this can be problematic when you're designing management interventions and allocating water resources, because you might over allocate or under allocate. So yeah, that's where some of the problems lie there with the coarse spatial resolution imagery. Moving on, you have moderate or high spatial resolution imagery. And these images generally capture a lot more detail about the specific region of interest, and they're particularly useful for applications at the field scale or local levels. So the coarse spatial resolution data, just to add further context to that there, the problems generally arise when we want to use it for very localized applications, small study sites, or applying it at the field scale. But if you were to apply it at a continental scale or at a country scale, you probably could get away with using this type of data. However, if we're looking at very localized applications, then yes, it's problematic. And this is where the use of moderate or high spatial resolution imagery would be preferred. The challenge that comes about with moderate spatial resolution imagery is that they are limited in their temporal resolution. So they're not frequently available. Data sets such as Sentinel and Landsat. Sentinel is available every 5 days. Landsat is available every 16 days. And then when issues such as cloud cover come up, the temporal resolution might be extended beyond what the sensor has been designed for. So in theory, if Landsat was available every 16 days and you had cloud in between, complete cloud coverage in between that, you could end up getting a Landsat image every 32 days, every 48 days, and so forth, just depending how unlucky you are with cloud coverage. So that there can be problematic when you're trying to monitor temporal progression or seasonal trends with specific hydrometeorological variables. Something that is not too much of a concern if you're looking specifically at hydrological data, spectral resolution, but it does come into play with things such as land cover mapping, which often is the backbone of many hydrological modeling applications and interpreting data. So it's important to understand some of the challenges with spectral resolution. So spectral resolution is essentially referring to the amount of information captured within the electromagnetic spectrum by the specific sensor. So if we just had to look at this image here, at the top, whatever sensor this represents, the spectral resolution is fairly low. So it's only capturing data in this blue, sorry. It's only capturing data within the blue, the green, the red, and let's call this the near infrared. So it's probably multispectral data. It's only got capturing information in 4 bands. So this means that we only have a certain amount of data available to us to distinguish certain characteristics about the land cover or area that we are interested in. If we have to move on to the second part of this graphic, we see that within the blue region now, there's a bit more detail that's been captured. Within the green, there's a bit more. Now there's a yellow region introduced. So now we're getting more and more data about this feature of interest or this area under observation. And when it comes to a task such as land cover mapping, the more unique characteristics we can acquire from a specific vegetation type of interest, it makes it easier to distinguish it from other vegetation types. So it allows for us to more accurately map certain things within the area under observation. So that's the trade-offs between spatial, temporal, and spectral resolution in a nutshell. I've run through them quite quickly, but they're very important concepts. So if anyone would like me to go back and explain it a bit better, please let me know before I move on. Okay, cool. I take the silence as I did a decent job. Okay, so we know about all the advantages associated with the use of remote sensing data, and it's great for a number of things. However, there are limitations associated with the data set, and not necessarily focusing on the conceptual limitations of how certain algorithms are designed to capture information that's required, or the spatial, temporal, and spectral resolution of the data set, what challenges are faced there. Those have specific techniques which can be adopted to aid in overcoming those limitations. But often the biggest challenge that we face, especially from a developing country perspective, is that we lack the capacity and the resources to adequately utilize this data. And that's mainly down to computational limitations. So remote sensing data has been captured over the past 4 decades or so, and now there's large volumes of freely available data that people can access for analysis. For example, if we had to look at just the Landsat 7 project, which commenced in 1999, it captures about 300 images per day, which is equivalent to more than 1 petabyte of data, or 1 million gigabytes. So despite the advantages and frequent use of this data for hydrological purposes, the handling and manipulating of large data sets can prove to be a major challenge. Furthermore, information technology management is often a stumbling block. So there's data acquisition challenges, storage challenges, computational power to actually process this data to get meaningful outputs from. If you just look at this graphic on the side, it's showing you the number of images captured across the globe and the yearly data volume of some of the different environmental sensors. How much more data is now available to us for analysis. So because of these computational difficulties, which have created a barrier for many people to actually access and utilize this data for several purposes, the project team at Google designed something known as Google Earth Engine. So this platform that is capable of storing and analyzing large volumes of data, which uses Google's own computing infrastructure. So Google Earth Engine can basically be described as a geospatial data analysis platform, and it's been specifically designed to provide users with access to an extremely large and diverse catalog of satellite Earth observation data with over 40 years worth of data, several data processing algorithms, built-in algorithms, as well as providing you with the ability to develop your own customized algorithms and run it within the platform. And everything is done within a programming interface, which can prove to be challenging when you are just beginning to work with the platform. But as you work through it, you'll see that there's several advantages to utilizing this programming interface. So some of the typical tasks that are performed in GE include acquiring an image or image collection with user-defined specifications, and processing these images or image collections using available algorithms or your own customized algorithms. You can compute statistics, export images, and export time series. You can upload your own data sets, which you can then process and take advantage of all the capabilities Google Earth Engine has. And you can also develop your own customized apps for sharing data. So I hope this link works, just to give you some insights into some of the apps that are available. Okay, so you do have access to this presentation, and if you click on the slide here under apps where it's underlined, it will take you to this web page that we're viewing now. If you come in here, this shows you the Earth Engine apps. It's dynamic, publicly accessible user interfaces for Earth Engine analysis. And these are some of the publicly available apps that have been designed. So these apps allow you to share your data and display them in a certain manner, which is easier for non-experts to view and appreciate and understand without having to get involved in the nitty-gritty of actually working with the codes. So just to go through them quickly, let's go through the linked maps. So if you click on this, it takes you to the app that has been developed to view linked maps, which are showing Sentinel-2 visualizations of a particular area of interest. And this is displaying data using different band combinations, which highlight certain features more prominently than if we were to use just the natural color RGB bands. So we can see at the top left here, this is the natural color. And yes, we can distinguish certain things. We can see that there's some water, some vegetation, some agricultural areas. But
apologies, Sabine.
Yes.
Sorry, I think we are not viewing a screen of what you're doing currently of the apps. We're only seeing the PowerPoint.
Okay, sorry, let me just change that.
Okay.
Screen. Okay, let me know if you can see it now.
Perfect. Now we can see it.
Okay, yeah, so if there are any technical issues that come up, just interrupt me and we'll try and address them as soon as possible.
Thank you.
Okay, yeah, so back to what I was describing. So in these images here, we can see on the upper left, there's this natural color image, and there's some agriculture, there's a river system, looks like there's some infrastructure in the area, but it might not be that easy to distinguish. So what we'll do is we'll use different band combinations, which highlight certain features for certain, for specific land use, land cover types. So we have this color infrared, which helps us now more clearly see the river system. We can see all the vegetation in red. We can see there's some infrastructure here in the side. This band combination at the bottom left here more clearly highlights what's land and water. And then the last band combination here more adequately shows vegetation. So this is just an example of how you can use one of these apps to more clearly display the outputs of your data processing. Another quite popular feature or app to use is the split panel map. So this helps you show comparisons between two different layers or two different data sets that you've been working with. So in this example here, you can pick an image that you want to visualize for a specific date range. So we'll pick this first one, and then we can compare it to another image at a later stage. So we'll pick the last one. And this is just showing this area and some surface water features. So we can see the river in here, and then you can swipe across and you can see how the landscape's changing and how the rivers and riparian areas changing as well. So again, very useful. It's just showing the output of the data, which is what is generally of most interest to people. They're not particularly, if they're not from a scientific background or aren't interested in the technical work that was involved, they just want to look at the data, this is a great way of sharing it with them. Just want to see. Okay, and there's the Global Forest Change Explorer. This is also quite a popular data set. So you can pick what you want to display in your maps. Okay, yeah, just to point out here again, these are apps which are taking the outputs from your Google Earth Engine processing and putting it in a format that's more user-friendly to visualize and interpret. This is just a feature of Google Earth Engine. It's not the Google Earth Engine platform itself. So just to make that clear, if anyone was unsure about that. Okay, so we'll look at another app that I've designed for one of the research projects that I'm working on a bit later. But now I'd actually like for us to go into the Google Earth Engine system. So before we actually log in and look at what the system is all about, I just want to run through the structural layout to get you familiar with things that you might be seeing when we log into the platform. If we begin at the bottom here, this is where you visualize the maps that you are importing or areas that you want to work with. You have these geometry tools which allow you to pan across the map, to add points, polygons, draw different features on the map. There's a layers tab here at the bottom, which displays the list of layers that you are currently working with or viewing. At the left-hand corner here, you have a script manager, which shows you all the scripts that are sitting within your repository. So scripts is just basically like a notebook of code that you have compiled to do or to perform certain tasks. You have API documentation, which is the built-in algorithms and processing procedures that Earth Engine has. And it gives you a description of the different requirements for those processing algorithms, as well as the line of code that you can just copy and paste into the code editor to actually run the processing task. Next to that, we have the asset manager, and the asset manager is basically a repository of all the information that you will be uploading into Earth Engine. So Earth Engine has its own repository or own data catalog that you can go and access data from, but in certain instances, you might want to work with a specific region of interest and you can upload a shapefile, or you might have an image that you want to process using Google Earth Engine's processing capabilities. So you can also upload it onto the platform, and the assets tab will show you all the assets that you've actually uploaded. You have a search bar here where you can search for data sets of places. You can get a link to the URL or script. So the script that you compile can be shared via this URL with anybody throughout the world. They don't have to necessarily have access to Google Earth Engine, although it is recommended because there's certain features that might not be available to them. So this makes data sharing and sharing of data processing procedures fairly easy. You have an option to save the script, you have an option to run the script. And when we actually get into the platform, you'll see there's an option here as well where it takes you to the app manager, where you go about actually developing your app, getting a URL for your app, and then being able to share the URL with different people to actually go and view the outputs of your data processing. On the right-hand side here, we have an inspector console. So the inspector console, you can think of as similar to the information cursor or tool that you have available within your GIS platforms, where you click on a certain area and then it provides you with all the relevant information for different layers in that specific area. You have the console. The console basically is showing you all the outputs of all the different processes that you are running. So you can display the names of the different layers you've added. You can show the outputs of, say, for instance, you've done a processing task and you want to generate a time series of rainfall for a specific area. you can generate that graph and plot it to the console. So all of that information is displayed and captured on the console. And then you have a task manager, which essentially shows you things that you are about to perform to extract data from Earth Engine. So for instance, after doing some processing on rainfall or ET data, you might have generated and created this time series. And now you want to take this time series and export it to do some further analysis on it. So you would have created or you would have written a piece of code to facilitate that process. And when you run it, the code doesn't actually automatically create the CSV file, or it doesn't automatically create the GeoTIFF image that you want to work with. In the task manager, it shows you that this is the task that needs to be completed, and then you execute it within the task manager. Okay, so quite a lot in a very short space of time. At this point, we are ready to actually go into Google Earth Engine, but yeah, before we proceed, please let me know if you'd like me to discuss anything else in further detail or to provide further examples or go through things a bit slower. Okay, I'm going to take it as we are all on the same page. I'm just going to close the presentation. Can everyone still see my screen?
Yes.
Okay, did everyone manage to get authorization to access Google Earth Engine? Has everyone registered for it? If anyone hasn't, just let me know, but yeah, you should be able to follow along and do most of the tasks once you acquire authorization, so it's not a big issue. Okay, so to access Google Earth Engine, you can just type Google Earth Engine within the Google search platform, and it should bring you to this web page here. Yeah, just to let you all know, Google Earth Engine is freely available, can be accessed by anyone. All you have to do is just sign up to the platform and get a Google user account, and that's it. Thereafter, 90% or more of the features available within Google Earth Engine are accessible to you. There are some unique features which have been specifically designed for developers to work with. So when you're at a more advanced level and you can contribute further to some of the services Google Earth Engine provides, then you get access to these unique features. But yeah, for basic users, such as myself, majority of what you require is available to you with your free access. So before we actually go into the processing platform, there's a video that is available here, which will summarize everything that I've discussed in a more aesthetically appealing and simple manner. Okay, so that short video is quite informative. It clearly demonstrates the capabilities of Google Earth Engine. And yeah, I think now let's actually go through it together and see what it's capable of. Yeah, so if you're following along, please log in. Okay, so everyone can still see my screen?
Yes, we can see it. I
All
can
right.
see
Yes,
it
we
from
can.
my side.
Okay, thanks. Yeah, so in the last slide of the presentation, I ran quickly through the structural layout of Google Earth Engine. But okay, what I should have done was on this home page showed you how to actually access this. So I've got a shortcut on my web pages that takes me directly to the code editor. But if you're starting off as a new user, once you've signed in, you see this platform here. And then if you go to the platforms tab, it'll give you an overview of what the Google Earth Engine is about, but where you actually perform your analysis is in the code editor. So if you click on code editor, it will bring you to this page here. So this is the actual Google Earth Engine JavaScript environment. So the coding language that is primarily used is JavaScript. There is Python scripting, which is available to users. I'm not too familiar with that, and JavaScript is quite popular, and you can do majority of the tasks that are required. The Python scripting is for more advanced analysis, which is not the focus of many users. So yeah, for now, we're just going to be focusing on JavaScripting. So within the Google Earth Engine environment, we have, as I mentioned before, the scripts panel or tab, and this shows you all the different scripts that you have compiled and saved, and you can easily access this whenever. So the nice thing about the scripting environment is I could have compiled a script to perform a specific task on a specific data set, and then at a later stage, I want to do some processing on a completely different data set, but there are some similar tasks which I want to perform. For example, filtering the collection for a specific region, calculating the mean for a specific region, plotting a time series. All I have to do is go back to one of the scripts that I've previously saved, copy out that chunk of code, paste it into my new script, and then rerun the task. It's very simple. The learning curve is a little bit steep at the outset when you're trying to understand how to set up your scripts, how to track errors using the correct syntax and so forth. But once you get a handle on that, it becomes very easy to do a lot of repetitive tasks on different data sets. And there are tons and tons of video tutorials and actual written tutorials which take you step by step through the different processes that you can, or the different tasks that you can perform in Google Earth Engine. And they also give you access to their processing code. So while those specific tasks might be designed to work within a specific area, you can easily take that code and adapt it for your specific purposes. So it's really nice that there's all of this support available online. And another useful, so I've provided a Word document that has links to several different useful resources that you can go through to show you how to access the different data sets, how to develop apps, how to do specific processing on the data. So if you're not working with satellite data products, but you want to work with the raw data to develop your own products, there's tutorials guiding you through the different processing procedures. One of the links which I didn't provide, which is also extremely useful, is a link to a website called Stack Overflow. Stack Overflow is basically used for troubleshooting with anything related to programming. So if you have some issues with your script, you don't know how to structure it correctly, or you're trying to perform a certain task and the script is just not working the way you'd like it to. You can copy your script and then go on to Stack Overflow. You paste it over there. You clearly describe the problem that you're experiencing. And then one of the developers that from anywhere throughout the world will respond to you, explaining where the error is, providing you with the correction to your problem. And they generally provide you with feedback fairly quickly, like within less than a week. So it's a really useful platform for you to engage with people when you're experiencing any issues. Okay, so back to the scripts tab. As I was saying, there's several scripts here that the owner will have. There's writer scripts, there's reader scripts. So some of the tutorials that you go through, people will give you access to their repositories, which will provide you with the code to perform some of the examples that they have within their tutorials. Some of these will be preloaded when you log into the system, but others you'll have to actually go to that specific tutorial and they'll explain how to upload their code repositories. There's the archive, there's example scripts. So some of the common tasks that you'd perform, for instance, on an image, if you want to get the Ndvi, which is the normalized difference vegetation index, they give you an example of the script to work with. So there's a lot of user support available within the platform without you having to actually turn to external resources. There's this documents tab, which has a list of all the different functions or processing tasks available within Earth Engine. And yeah, if you had to expand these, and for instance, let's look at Landsat. So within Landsat, if we wanted to do a conversion to get calibrated radiances, we'd call up this function ee.algorithms. We'll specify the image you want to work with, and it'll perform that function. So you can just copy this across and paste it into your scripting environment. You also have your assets. So your assets are things that you would upload to the system. So this should be empty for all of you, but if you want to upload stuff, you click here on new and it gives you different options. So you can upload images that you want to work with. You can upload tables. So tables generally would be capturing the vector data. So Google Earth Engine is primarily houses raster data sets. There are some vector data sets for you to work with. But yeah, majority of it is raster data. So if you are interested in doing processing on a specific region of interest and you have a shapefile for it, you can always upload it onto the platform and then access it by just writing a few lines of code. You can upload entire image collections, so you don't have to only upload a specific image. If you've got a collection of images from a specific satellite Earth observation data product, you can upload those as well and do processing on them. You have your actual coding environment or your scripting environment here where you write the code to perform the different tasks that you are interested in doing. You got this get link button here, which will give you a URL, which you can then copy and share with other people to share your code, to view the code. They can run certain parts of the code. In certain instances, if you're working with specific data sets that you've uploaded onto the platform, you have to make them publicly available first before they can be run with whatever code you've designed. More often than not, though, you work with publicly available data that's housed already on Earth Engine. So getting the URL and sharing it and allowing someone else to run that code in the same manner shouldn't be any issue. You can save your code. So as you're going along and you're making changes and certain modifications to your different codes, you can save them, and yeah, they'll save in a folder for a specific project. This is to actually run the code. To reset the code, the apps button here takes you to a place where you can manage your apps. So I've already developed an app here which helps visualize the output of a land cover mapping exercise using drone imagery. So just to show you quickly, so drone imagery is not available within Earth Engine. This is an image, an RGB image captured, but not an RGB image, a multi-spectral image captured over a smallholder farm that we've been doing some research on. And while it's easy to, now it's zooming in, zoom out. Yeah, while it's fairly easy to visualize or to distinguish the different land use, land cover classes here just by looking at this image, if I wanted to do some hydrological modeling analysis or some interpretation of a different data set against the land cover present in this area, it makes it a bit difficult to do using the data like this. So having a land cover map to work with makes it much more easier to perform certain tasks. And it also provides us with a reference condition where we can compare changes over time against. So that was the purpose of designing this land cover map. And I ran different processing procedures within Earth Engine to aid with this task. And the output is something like this. So from developing this app, I don't have to actually share the code with people and show them all the technical details that went into generating this map. I can just show them, okay, from this drone image, when you perform certain processing tasks, this is the output that you can generate. And then, yeah, users can swipe across different regions to look at, okay, where's the grassland, where's the agriculture, where are the buildings and infrastructure. And yeah, I perform this classification at different spatial resolutions. So this will also more clearly highlight some of the spatial resolution. Oh, sorry about that. Yeah, so this will more clearly demonstrate some of the issues that come up with using coarse spatial resolution data in a spatially heterogeneous environment. So let's just zoom out a little. You can see there's clear differences between bare soils, grassland, some of these shrubs, the agriculture, etc. And this is quite well captured at the 7 centimeter spatial resolution. At a 0.5 meter spatial resolution, you see things start changing a bit now. And then at a 5 meter resolution, it's hard to distinguish exactly which land use, land cover is where on this image. And previously, like a lot of the areas where you could clearly distinguish between, for instance, trees and shrubs and bare soil, at the fine spatial resolution, you can no longer do that at this coarser spatial resolution. So this is just to demonstrate the advantage of having this high resolution data, which is something that's required for these smallholder farms given their spatial heterogeneity. So that's just an example of an app. As I said, you have this inspector console where you can click on the map and then they'll provide you with certain information about the layers that are present. So for now, it's not giving us any further information beyond the geographical coordinates and the scale that we're working at. But if I were to add a hydrometeorological data set or any other data set in here, it would start providing information about the data in this inspector tab. The console shows us all the different, shows us the output of all the different processes that we're running. The tasks are where we'll see what tasks we're about to perform when we run this code. So for instance, are we exporting data in a specific format, be it CSV, are we exporting an image, etc. It'll all come up here in the task manager, and then you have to physically click on a run function, and then that will actually execute the task and export the data to, in most instances, it'll export it to cloud storage, but you can specify other options. And here, and here at the bottom, you have the actual map layer that shows you the area that you're working with. And you can zoom in to display your data set. So it's showing only a region of interest and you don't get any of the background data that's being displayed. Okay, so this was a very quick overview of the structural layout. And I think we've been going for about an hour now. So does anyone want to take a 5 or 10-minute comfort break and then we get back into the actual processing on the platform?
I think the break will do.
Okay, it's now 11:06, so 11:15 we resume.
Okay, that's fine.
Okay, cool. See you shortly. Okay, so before we actually start engaging with the platform, does anybody have any questions? Gone through quite a bit of content and can be a lot to digest and be a bit overwhelming. So please feel free to ask questions.
I'm looking for the icon to raise my hand. I got in the middle of the class, but then I wanted to check, how does Google Earth Engine work with Google Earth Pro?
Okay, so they're two separate platforms. Google Earth Engine is specifically designed to work with the processing of the satellite Earth observation data. Google Earth Pro is more for visualizing, for instance, like a RGB image covering a certain area. There are certain things that you can do, which you can then bring into Google Earth Engine. For instance, if you want to create a shapefile or a boundary of a region of interest that you're interested in, you can start by going into Google Earth Pro, navigating to the area that you want to work with, creating a shapefile in there, saving that, and then uploading it into Earth Engine. But yeah, they're two standalone platforms. So the things that you do in Google Earth Engine are very different to what you do in Google Earth Pro.
All right, thank you so much.
You cannot use G when you have. Okay, so there's a question here about using GE when you have scripts and data sets. I'm having a little bit of difficulty understanding the question. Maybe if you can ask it verbally. Oh, okay. Yeah, so that's one important feature of GE that I should have mentioned. So GE doesn't use any of your actual computing resources. So you don't have to have a highly sophisticated machine to work with GE and perform the processing. Everything is done on the fly in the cloud, but it's really important that you have a strong internet connection. So that can be one of the main limitations of Earth Engine, is that it's dependent on you having access to the internet. I hope that answers your question. Cool. Any more questions? I much prefer to respond to questions rather than telling you things that I think you should know. Okay, so if I don't see a question come up in the chat, or I don't see the icon where you've raised your hand and want to ask something, just ask it verbally and interrupt me whenever you feel like it. Okay, so let's start going through some examples of what you can do in Google Earth Engine. So can everyone see my screen?
Yes.
Okay, thank you.
Yeah, we can see it.
Thanks. Right, so in Earth Engine, we went through the structural layout, and this part in the center here is where you actually do your scripting, so you can type in the different functions that you would like to work with. But a lot of the time, you might not know how to correctly access a data set or what the data set contains, and you want to actually go and search for a specific data set to work with. So the difference between Earth Engine and some of the other platforms where you access the satellite Earth observation data is Earth Engine will give you direct access to import the data to actually do the processing with it. But the way it's designed is that you don't have to physically download images upon images upon images to work with and excessively utilize the resources on your computer. Everything is housed on the cloud. You access it from the cloud, you do your processing, and then you only export the final output. So it's only the data that you are interested in sharing with other people. So yeah, let's have a look at what's available in the catalog over here. So if I type in rainfall, you can see there's a list of different rainfall data sets. If I click here on more, there's a whole repository of different types of satellite Earth observation data. And in some instances, there's model data that's stored in a raster format that's available for us to access. Not sure if you've already gone through the GLDAS platform, but yeah, so GLDAS might have a specific platform where you can access the data sets and work with, but the data is also housed on Google Earth Engine. So if I wanted to access the GLDAS data, I can just type in GLDAS, search for it, and then it shows the two different GLDAS data catalogs that are available. If I just click on 2.1, I get a brief summary of what the GLDAS data entails. And if you see here where my cursor is, there's this icon on the top right-hand side with an arrow. If I click on that, it expands and now provides more information on what the GLDAS data set entails. So it gives you a description of the data set. You see the bands that are available, or all the different types of data that is housed within this GLDAS catalog. If we click on image properties, it tells us, it gives us further information about the characteristics of the data. It explains the term of use and what's often required for your scientific publications. And when you're writing up reports and things like that, there you need references to the data set. So it provides you citations of the formulation papers where they describe how the data was created, and also in some instances you get examples of where the data has been used. So expanding upon the data set is quite useful. And yeah, at the bottom here, they give you snippets of code. So you might not be familiar with how to actually go about accessing the data and processing it. So you're going to require some form of template to work off and then visualize the data and do further processing. So if you're a complete newbie and you just want to see what the GLDAS data is all about, you can just copy this code in and go back to the code editor. So if I just paste this code in here. So this is the script that one would compile to do certain processing on the data set. And the way it's structured is we have to declare certain things that we want to work with as variables first. So right at the top here, you have a variable called dataset. So that's the dataset that you're trying to access. And there's a specific function in Earth Engine called EE image collection. And this is going to help us import an image collection. So you can either import an image collection or you can import an image. depending on what you are trying to do, you'd import the image or the image collection. But let's say, for instance, you want to get long-term time series of, in this example here, it's temperature. So you want long-term time series of temperature. You'd call up the image collection, and then you'll do a little bit more filtering on the data. So you only acquiring information for probably for a specific region, for a specific time period, and you can use all of these different functions in there to actually filter the data set to give you only the information that you're interested in. So this is a global data set, and if we had to run the code as is, it is probably going to give us all of the temperature information across the globe for the specific time period. There's additional filtering that you can perform where you only access data for a particular region of interest. And in most instances, that's what you do. So you don't want to access any unnecessary information that's going to prolong the processing time. You want to make things as efficient as possible. So you apply a number of filters into your script to allow you to only work with the data that you're interested in. So over here, we've got this variable data set. We call the function image collection. And this is the title of the data set in Earth Engine. So just move this down. So if you come here to GLDAS, and we go under the description, let's just close this. If we didn't go into the expanded description and you just went to the brief overview, you see here it says collection snippet, and this is how you access the image collection. So you copy this name in, and then you paste it into your code editor. So we're calling up the GLDAS data, and we're applying a date filter on this. So now we're only accessing temperature data for the 1st of June in 2010. So within this data set, as we just saw, and I'll show it again now, there's a number of different bands which have data on different variables of interest, but we don't want to access all of those variables. We're only interested in the surface temperature. So we create another variable called, in this instance, they've called it average surface skin temperature. And we're going to apply a further filter to it where we're only going to select the temperature data. So at the outset, the entire image collection we've called data set. And now we're going to filter this data set further to only get the information that we're interested in, which is temperature. So to data set, we applied a filter where we're saying select, and we only select temperature data. Thereafter, we can specify some visual properties for this image we're about to import into Google Earth Engine. And this is just a color palette. The color palette over here is different alphanumerics are HTML code that represent a specific color. So you can use the predefined color palettes, you can import specialized color palettes, or you can just go in to Google and just type HTML colors, and then it will give you the HTML color codes. So you can create your own unique color palettes if you want, just by doing this and copying the code across and pasting it in here. You can, for visualization purposes, you can center the map or zoom into a specific area of interest. So at the moment, we're not applying any filter by region, so it's not going to automatically provide the data and zoom into the data for that region of interest. So by providing these coordinates, it's now going to just zoom into an area that we can focus on. And then, yeah, finally, you add another function, which is actually going to add the layer onto the map for visualizing. So I'll just show you, if we had to remove that and we ran the code as is, and we look in the console, nothing appears. And that's because we haven't specified that we want to visualize the map. So by adding that in, I'm just going to add one more function here. Okay, so let's rerun this. So just like that, we've got our temperature data. So in a matter of seconds, we've accessed the entire image collection. We've filtered it to give us only a specific variable of interest. We've designed a color palette for display purposes, and then we've loaded this data here. So this ran fairly quickly because we filtered it only for 1 day. If you were going to do a more, if you're going to work with a longer time period, it probably will take a little bit longer to run. And when you're performing certain tasks, there is a computational limit which Google allows for users that are working with the freely available version of the platform. I think that's, you can't access information for more than 5,000 pixels or so without specifying a different upper limit for the processing. So in those instances, the computation may time out and not run and provide you with your output. But yeah, for most of your tasks, you shouldn't come across that issue. This function I've added here at the bottom called print dataset. So this is just going to give us information about the dataset that we've just imported. So print dataset is referring to this dataset right at the top here. So prior to the filtering, where it's only been filtered for date and nothing else. And then we've specified that when we're printing this data set, or when we're printing the information about this data set to the console, we want to be able to identify what it is. So we've called it temperature here, and you can see in the console at the bottom, there's the image collection that we're working with, and we called it temperature. If I click on the arrow here, you expand it and it provides you with further information. And in here, it's showing us that for this specific area that we zoomed in, there's 8 images. So they listed from 0 to 7. And within each one of these 8 images, there's 36 bands. And these are the different variables that are stored within that particular image. I see there's 2 questions on the chat. I'll get to that now. I just want to run through this quickly. Okay, so over here, we've printed the entire image collection. So it's got all 36 bands that are available in GLDAS. So it's all of this information here. Just to make sure that our filtering process works correctly and we're only displaying temperature, I'm going to print another output to the console. So I'm going to print this variable called average surface skin temperature, where we've only filtered the data set to show us temperature. So I print that in and then give it a name. Let's call it temperature 1. Run the script again, and we see now that temperature 1's come up. If we expand this again, there's 7 images that are being displayed, but now each one of these images only contains the temperature information. So you see the bands, there's only 1 band with temperature, whereas with the original image collection, for that specific image, there were 36 bands. So that just gives you an indication of how the processing is working. So it's quite useful to print the output of certain processing procedures to the console just to ensure that everything is running smoothly. Sometimes you might have made an error in your script, which won't cause the script to bomb out. It will still run and produce an output, but it might not necessarily be the output that you're interested in working in. So yeah, printing stuff to the console and then viewing the data there just helps you ensure that things are progressing the way you'd like them to. Okay, let's get, what does min 250 and max 300 mean? Okay, so in this instance here, because we're working with temperature data in Kelvin, min is the minimum temperature in Kelvin and max is the maximum temperature in Kelvin. So the color palette is going to stretch across the values from 250 to 300. If we specify a smaller color palette, so I can just do this for demonstration purposes here. Let's make the color palette 280. And I'll just run it, and now you'll see the visualization changes. So depending on the min-max that you specify, it'll affect how the color palette is assigned to certain values, which then in turn impacts the visualization. For use in GE, is it necessary to be good in programming? Being good in programming is obviously an advantage, specifically if you've got experience with JavaScripting, but no, you don't need any prior knowledge of programming to work with GEE. As I said, there will be a bit of a steep learning curve when you first working with the platform, but you'll easily overcome that as long as you dedicate time to it. I've had no prior experience in programming, and within a period of 2 to 3 months, just working with the platform, working through the different tutorials, using Stack Overflow, I've managed to accomplish quite advanced processing tasks. And what I would say is the most important thing is being able to read and understand the code. You might not know all of the functions and the processing algorithms available to you, but if you can read someone else's code where they've done similar things and understand how to copy it across and how to modify it for your specific purposes, that's more than enough. So you'll find a lot of times that you want to, say for instance, you've got this data set and you've calculated the normalized difference vegetation index and you followed a certain procedure and you're comfortable, you know how to do that, but you also want to add on an additional vegetation index, maybe the enhanced vegetation index. And the formula or the calculation is different to the Ndvi. So it's just a minor modification in that calculation procedure where you go and change certain input variables or certain coefficients that you use in the equation, and then you run the script. So it's most of the time you'll be using pre-existing scripts and then making minor modifications. When it comes to more advanced analysis and when you're developing apps and things like that, that's where it starts getting a bit more complicated. But again, there's enough user support available online for you to overcome any issues that you're experiencing. I saw someone had their hand raised and it went back down. Yeah, sure. I see the hand raised again. You can go for it.
Yes, I wanted to ask, on that same code that you just used, is it possible now to, if I want to focus on a particular area, is it possible to modify it?
Yeah. So I'll go through all of those examples shortly. This was just the first one. So these are the snippets of code that I'm pasting in here just to show you this is what's readily available to you on the platform, just to visualize the data and view the data. So if you're working with this live and following along, we can type in almost anything. Let's go with rainfall. So this first example that we went through was for the entire GL data catalog, and we visualized a particular variable from that catalog. Now we'll be looking at a rainfall product. So I think from your discussions with Ms. Chetty, she might have given you several examples of different rainfall products that are available. Not all satellite Earth observation data sets are stored within Earth Engine. So just be aware of that. There might be some data sets that you might be interested in using, but they're not available in Earth Engine. However, if you are able to access them and download them onto your local machine or hard drive, you can always import them and run the same processing procedures within Earth Engine. So that's also a nice thing about it. I think the most well-known rainfall data set is TRIM. Instead of working with the hourly, let's work with the monthly, just so it speeds up the whole processing. So I've typed in rainfall, we've searched for TRIM. We can see monthly precipitation estimates. So you can see there's the snippet of code here, or this is the name of the image collection. There's the bands in here. So we have precipitation. The units are in millimeters per hour. We have the relative error, the gauge weighting, and so on. So, sorry, that's the wrong one. So let's expand it. Okay, and there's the snippet of code here for trim. So I'm just going to copy that across. Doing this now. I just need to move things about to close that. Okay. Top. Okay, so you can just delete stuff. Obviously, if you are working with something important, save it first and then delete, otherwise it will just clear out. Okay, so back to the trim data. So monthly trim data. We've called up the image collection. Again, we've declared a variable called dataset, which houses all the trim data. We run the function image collection. There's the name of the entire data catalog. We're filtering it for date, and now it's filtering it for a month. Well, it makes sense because it's monthly data. Yeah, within the data set, remember there were 3 different bands. We're only interested in the rainfall. So when we can apply a filter and say data set select, and we only select the precipitation. There's some visualization characteristics, and these colors need to be stretched over a minimum value of 0.1 to a maximum of 1.2. We can zoom into a specific area of interest and then add the layer to the map. And I'm just going to add the print function here to ensure that we are adding the correct data set. So print precipitation. In the previous example, I didn't explain it, but I will now. So when we call up the print function, the first input is the data set that we want to actually print to the catalog. So we're printing this precipitation data set that's been filtered. And when it appears on the catalog, we want to have a specific name associated with it. So I've called it precipitation here. And if I run, so quick as that, now we've got monthly rainfall. And yeah, it's monthly rainfall for the entire globe. You can navigate, zoom in, zoom out just for visualization. Let's go into South Africa. And yeah, to demonstrate the inspector console. So if I click on a certain point, it is now telling me precipitation from Mosaic. There's the precipitation value, 0.12, 0.2 millimeters per hour for the month. So that's the average monthly precipitation rate. In the layers tab here, it's showing us exactly which layer is being displayed. Sometimes you'll have multiple layers that are present, and you'll have a whole list over here of the different layers. You can switch it off so you can visualize the map of where you're working. Switch it back on. You click on this gear icon here, just gives you the visualization parameters. So we specified a custom palette. You can also just stretch it entirely across the range of values and work with the predefined color palette, or you can go in and pick your own colors, but let's just work with the predefined one. Just go apply, and it's changed. Okay, so any questions thus far on this, how to just copy code snippet and quickly browse through the data? Okay, so these are just very basic things that you can do when you're viewing the data. Trying to, let's pick the data set. Yeah, so just to show you, and I expanded using that icon, this gives me more information about about trim. If I click here on view all data sets, it will now show me the entire catalog of data that's housed on Earth Engine. You can see there's LiDAR data, there's DEMs, land cover maps, outputs of models, outputs of climate projections, raw MODIS data, Landsat, Sentinel, the entire archives of these data sets, which are commonly used for hydrological and environmental analyses. Yeah, there's another nice feature about Google Earth Engine, and specifically using the examples of MODIS, Sentinel, and Landsat. A lot of the time, if you were to access these using the traditional or conventional data access portals and platforms, you'd be accessing the raw data, which still requires some pre-processing to perform atmospheric corrections, radiometric corrections, etc. And that's all required to get meaningful outputs from your data. So you have to do that first before you start actually doing further processing. Within Earth Engine, they provide you access to the raw data, so the data that needs to be processed or pre-processed, but you also have access to the processed data. So you can start working with the data to generate those meaningful outputs without having to worry about first going through all that pre-processing. So it makes things a lot easier and speeds up the whole data analysis process. Just scrolling down, there's soils data, descriptions of terrain units and landforms. There's reanalysis climate data. So similar to how GLDAS provides you with a number of different hydrometeorological variables, this ERA 5 does something similar at different time steps. There's hyperspectral data. So hyperspectral data is generally quite expensive to acquire and is not readily available, but Earth Engine does have some of this for specific regions available. There's land cover data, as I've mentioned. There's administrative layers. So this is more your vector data if you're interested in, instead of having to import a shapefile or upload a shapefile before you use it, you can call up administrative units for certain areas and then extract information for a particular boundary. There's ET data, number of different ET data sets. And these are ET products, so there's no processing required on your part in terms of taking the raw satellite data, running it through some energy balance model or vegetation index model to generate the ET data. This is readily available ET data for you to use. Yeah, and quite a large number of outputs, or a large number of data sets rather. Okay, so can anyone think of a data set offhand that they'd like to visualize quickly before we start looking at some other processing examples? What are some of the common data sets that are of interest to you?
Can I suggest net primary productivity?
Okay, so net primary productivity, NPP.
Yes.
Yeah, so if I just type in NPP, because let's say I'm not familiar with which specific product I want to use, but I know I'm interested in net primary productivity, I can just type in NPP or net primary productivity and it'll give me the whole list of data sets which could be related to that search term. It's not always the case that it will come up with a net primary productivity data set, but it's something that is related to it. So if we look at the first part, we see that there's Landsat, there's MODIS, but this is only for the US. So that's probably not of interest to us. Then if we scroll further down, we see, okay, there's the MODIS Terra product. So MODIS has aqua and terra data, and the terra data is captured during the early parts of the day. The aqua data is captured at later parts in the day. And then you also get like an average between the two, but it's not available for all of the MODIS data sets. It's just some of them. There's the WAPOR data set. And yeah, so there's advantages and disadvantages to working with each of these different data sets. Obviously, the models that are used to generate this data, their conceptualization is based on certain assumptions, which might hold true for certain regions and provide you with accurate data, whereas in other regions it might not work. So you got to do a little bit more research prior to selecting a data set. Don't just pick the first one that you think is fit for purpose. Understand the objectives of your study and what you're trying to demonstrate before selecting the data. Also, another thing to factor in is the temporal resolution of the data. How often is it available? Are you trying to do long-term time series analysis? The spatial resolution. So you can see there's this gap filled yearly 500, there's 500 to 1 kilometer. So let's just view the MODIS quickly. Talking a bit too much without demonstrating. Okay, so we clicked on that. We can see the description provides information about net primary productivity at a 500-meter pixel resolution. So if you are going to use this for national level, continental level, the spatial resolution is probably adequate. If you're looking at a specific forest compartment in a particular region, then probably not the best data set to work with. The bands that are present in here is your net primary productivity. It gives you the units. Something important to note, which wasn't in the previous data sets, but in some data sets, there's this thing called scale. So it's a scaling factor. So the data is stored, for instance, if we're looking at ET might be stored in values that are multiplied by 1,000. So if you were to use the data as is, you'd get excessively high values, and that's problematic. So it's important to be aware of the scale. So the scale function needs to be applied to the data set to get it into the units or the values that you are interested in working with. So yeah, just remember that. Now let's actually view the data. Do that. Run it. Okay, and then there's net primary productivity. So because for this one, we didn't specify a date range, you can see the data is available from 2001 to 2020. So it's either taking the first image available in the collection or the last image. So just for visualization purposes, it's not an issue. But if you are trying to access time series information and things like that, then you probably want to apply a date filter. So you're just getting values for the period you're interested in. I'm just going to scroll down a bit further so you can more clearly visualize differences in the net primary productivity. Yeah, if I click on a region, so let me just switch this layer off. Okay. So this NPP value is probably excessively high compared to what you'd be used to seeing, and that's because the scaling factor hasn't been applied. So you can multiply, you can use the multiplication factor as a function directly in Earth Engine, which involves adding a few more lines of code. Alternatively, if you're exporting the data as a CSV, or if you're just exporting this particular image, you can apply the scaling factor in something like Excel, or if you're working with the image in QGIS or in ArcGIS, you just apply the scaling factor there. So it's fairly straightforward. And this is showing us all the different values, so you can see how it's ranging. Okay. Any other data sets? All right, let's go through some of the data sets that I've worked with. Let's see. Okay, so we started with GLDAS, and then I mentioned rainfall data. So I'm just opening up a script that I've previously worked with. Let's delete some of the stuff that's not required. Okay, so the first part of the script now is I'm defining the data set that I want to work with. So I've declared this variable called trim data set. This is a 3-hourly trim data. I want to access the image collection. I want to apply a date filter. So I want data from 2019 July to December 2020. I want to filter it. So I only want to have data for a particular region of interest. So this is a bit different to the previous examples. Now we're actually going to define a region of interest we want to work with. If you have a shapefile, you'll come into your assets, you click on shapefiles, you can select the shapefile that you're interested in working with. It'll tell you what extensions are allowed. You can assign a name to the shapefile and then you upload it. Okay, let me see, there's a question. GPCC. Okay, I'll have a look at that now quickly before going on to this example. Global precipitation. The GPCC data doesn't seem to be here, but it could be under a different name. I'll just have to look up on that. Okay, yeah, so back to looking at the data for a specific region. So in the previous code, we stopped at this point here at filter date. Now I've added an additional line of code, which is calling the specific task called filter bounds. And filter bounds is basically specifying a region of interest that you want to work with. And I've labeled the region of interest that I want to work with ROI. Okay, there's a request for elevation data. We'll have a look at that just now. Let me just run through this example quickly. So at the moment, I've got assets available in here that I can call up. So let's just see which is a nice one to use. Okay, let's leave that for now. So yeah, if you have assets that you've uploaded, you can click on the asset name. So I will go to a region that I've worked with previously. And if you click on the asset name, it will tell you, provide you all the details about the asset that you've been working with. So this is just a polygon somewhere in South Africa. It will give you the properties and so on, but you're not really interested in that. What you want to do is, once you've uploaded the asset, excuse me, you can click on this arrow here and it'll add the asset into the script. So without adding it to the script, you won't be able to access it. So it's important that you perform that step first. And yeah, when I've imported it to the script, it's given it the name table. You can leave the name as is. There's no issues with that. Alternatively, you can give it in. Again, the script probably won't be able to recognize it because it's in a separate component of the script and it's not in the actual processing. So if we want to work with that asset, we'll have to declare it. So I'll create a variable called ROI. And this variable ROI is bringing in this asset that we've just imported. And then the script will be able to run. So it will filter the data set for this specific date range for that specific region of interest. I'm only selecting the precipitation data from this 3-hourly trim. I'm giving it some visualization characteristics. Then I'm adding the layer to the map. I can remove this component of the script. That's not required. I'm zooming into the region of interest, and then we can create a graph of the time series using the specific function available here. So I'm just going to remove this region of interest now because it's a fairly small area and it's probably not going to work well, but I want to show you quite a useful feature in GEE. If you don't have a shapefile, but you know where your region of interest is. So I will work with somewhere around Pietermaritzburg, where I'm currently based. So at the bottom over here, where you're viewing the map, you see there's the hand icon for panning. There's a point which comes up with the name geometry. So if you click on geometry,
Afternoon. Afternoon, everyone.
Hello.
Hello, I think we've lost Shedun. Maybe he has been booted out, but he's coming back.
Afternoon.
Yes, good afternoon, ma'am. How are you?
I'm good. We are waiting for It's scheduled to reconnect. Can we all switch on our cameras for a group photo while we are waiting for him? Okay, thank you so much.
Hi everyone, sorry, load shedding issues.
Welcome back.
Okay, are we good to start again?
Yes.
Okay. All right, so when I got cut off, I was explaining that now we want to filter the data for a specific region of interest. We also only going to select the precipitation band from the data set. We applying some visualization characteristics to the data. We're going to add the layer to the map. So we're calling up the precipitation data set. We're applying the visualization characteristics. And we're calling the layer precipitation. And then quite often we want time series. We're interested in time series of these data sets for our regions of interest, either to make some quick visual analysis or to use as inputs for modeling purposes. So we can graph a time series and we can also export a time series. I'll show you how to do that shortly. And thereafter, I was describing how one would do the whole filtering process regarding using a region of interest. So if you have a shapefile that you'd like to use, you can always upload it using the function here available under the assets. Alternatively, if you know an area or region that you are interested in using, you can come down here into the map itself. There's the point icon where you can drop a point and it comes up as it would if you were to import a shapefile. So you see it comes up there and it comes up with the name geometry. So I'm just going to remove these. So you can drop a point, you can draw a line. Remove that because we're not interested in that. So most of the time you'd either be drawing a shape or using the point function. So I just want to draw a fairly decent looking polygon. Okay, so that now becomes a region of interest or a shapefile that I can use to filter my data and access it. So in our script, we've called it region of interest, but at the moment, it won't be able to identify it because the names differ. So in here, it's called geometry. In here, it's called region of interest. So I can leave the name as geometry if I'd like, but prior to running the script, I need to declare a variable called region of interest. And the region of interest is actually this geometry that we've drawn. And yeah, let me just run this now and see what comes up. So you can see now the processing is taking a little bit longer because we're working on a far longer period. That was still fairly quick, I'd say under 10 to 15 seconds. So in under 10 to 15 seconds, what it's done is it's gone through the entire trim data archive. It's extracted 1,471 images. Within these 1,471 images, it's then acquired data for each time period. And yeah, this graph that we're plotting over here is showing us the mean value for this specific region of interest. I'm just going to switch the background layer off because I didn't clip it just to display for this region of interest. But this graph here is showing us the mean rainfall or the mean 3-hourly rainfall in this particular region. Similar to how we expand the catalog when we're viewing the data, you can expand this graph. So you can see it more clearly here. So this is the 3-hourly rainfall rate. You can specify the legend and yeah, the x-axis legend, the y-axis legend, and so on. But what's of what you'd really be interested in here is actually accessing the data. So one way of doing it, when you have a fairly short record that you're working with, is when you expand this graph here, you get this option called download CSV. So if you download the CSV, you're going to get the data in CSV format. Download PNG, you'll get the graph as a picture format. So this graph is not that aesthetically appealing, so you probably wouldn't want to download the PNG, but let's download the CSV. And yeah, I've got fairly good internet connection, so it's downloaded almost instantaneously. Let's move this, and there we go. So Earth Engine has its own unique format of storing dates and time. So when you're plotting graphs and things like that, there sometimes you can easily manipulate the date and time in Excel and there'll be no issues. Otherwise, you have to have some additional functions that you include in the script to convert the date and time into a format that is easy to use when you export the data. But for now, you shouldn't be too concerned about that. And as you can see, so for the 1st of January, the 3-hour average rainfall in that specific region from 2019 all the way to the end of December 2019. So in a matter of seconds, we've generated time series data from these 1,471 images. I'm not too sure how familiar everyone is with accessing this data and processing it, but I'm sure this is far, far faster than what you'd have done traditionally. Okay, so there were 2 questions, and unfortunately these disappeared when I got disconnected. So can you please post them again or ask them now? And also if you have any questions about what I've just done here with the data processing, let me know. Switch my video off. Okay, what should the coordinate system of the polygons be when you upload it? Okay, so the nice thing about Earth Engine is that you can use any coordinate system. The Earth Engine has its own reference coordinate system that it works with. So whatever data you upload into Earth Engine, it will convert it to the native coordinate system. You can do all your processing and you don't have to worry about getting all the data sets in the same projection. It will do all of that on the fly for you. But when you're exporting the data, especially if you're exporting an image, that image will be exported in the Earth Engine reference coordinate system. You have to specify the coordinate system that you're interested in working with, and it's not difficult to do. It's just like a line or 2 of code, but it's something that you have to do if you want to work with data in a specific coordinate system. And it also has its own naming convention for the different coordinate systems. So something like WGS 1984 or Universal Transverse Mercator, etc. That naming system won't be displayed in Earth Engine. So I'll show you an example now where we can actually view the coordinate system. But yeah, to answer your question, when you're uploading data, no, it's not necessary to use a specific type of coordinate system. It just needs projection information attached to the data. Okay, so I hope that answers your question. The next question is regarding a DEM. So can you be more specific about what you'd like to know about the DEM? And then I'm just going to go on to the next question while you adding some more information there. Thank you for the presentation. May you please share some of these scripts, especially the current one. Okay, so what I can do is we'll compile a script together for TRIM or any one of the other rainfall data sets, and I can share that with you. But yeah, there's also plenty of scripts that you can copy and paste into your code editor and work with from those useful resource links that I provided. So don't only focus on what I'm doing over here, because I have fairly limited knowledge about the capabilities of Google Earth Engine. There's a way more that you can learn. So please go through those resources. The things that I'm demonstrating here are tasks that I've undertaken for specific purposes. So some of these things might not be of interest to you, but if you're only following what I'm doing, then you're getting a very narrow view of what Google Earth Engine can potentially do. All right. Yeah, the question on DEM. I don't know if he's still with us or he's shy. Okay, so just I'm going to wing it here and type in DEM. So if the question was pertaining to what type of digital elevation models are available, if you just type in DEM, this shows you all the different types of DEMs available. Some of the DEMs over here are derived from LiDAR data. So you've got these very fine spatial resolution DEMs, like for instance, this Australian DEM is a 5-meter resolution. But generally, your globally available products are, I think the finest that's available here on Google Earth Engine is from SRTM, which is 30 meters. There is another data set, so it's this ALOS Pulsar DEM, and this is 12.5 meter. Unfortunately, this DEM is not housed on Google Earth Engine, but it's fairly easy to access and it's freely available. So this is 12.5 meter resolution versus 30 meter, which is what's generally available. This ALOS Pulsar also is global coverage. So yeah, if you're interested in a finer resolution DEM, you can give that a look. Okay, any other questions thus far? Okay, so let's look at another example. So this was rainfall. Let's look at ET. Okay, so in here, I've already specified a region of interest that I want to work with. So this is one of the study sites that I was undertaking some research on previously. Okay, before I carry on, there's a question. Okay, so you wanted to know whether you can do any additional processing on the DEM. Yes, you can do additional processing. There might not be predefined processes that you can just call up as functions, for instance, like how we call up the filter function and so on. But you can write expressions in Earth Engine to perform certain calculations. And there are probably a lot of people that have attempted to do whatever task you're interested in doing. They probably have attempted to do it in Earth Engine. So just use those search terms, processing DEM data in Google Earth Engine, and see what it throws up. People usually provide the code. So all of the stuff over here is meant to be freely available, and there's a wide community of practice where people want to support each other's research. So they generally make these things freely available. If it's not freely available on the net, you can contact them directly and they probably would share the code with you. Because none of this is used for commercial purposes, it's mainly meant as a research tool. People are happy to share data sets and processing procedures. So yeah, you can have a look at that. Otherwise, if you want to do things like process your DEM to get flow accumulation, flow thresholds, define catchment boundaries and stream flow networks, you can just download the data, and then within QGIS and ArcGIS, there are modules available that can process it further for you fairly easily. Is there code on elevation and temperature? Yes, there probably is. It just depends which data set you want to work with. But when you're going into the data catalog and viewing those data sets, those code snippets that are provided are just to view the data. If you want to do something specific to that data set, like how in the example I've showed here with the trim data, where we wanted to get the average value for a region of interest, then you'll have to look up. So you're going to have to search on Earth, on Google, specifically clearly stating what you're looking for and see what the search throws up. Alternatively, you're going to have to extract different parts of code from different tutorials and compile it together into your code to perform a certain task. So I'll show you an example now when we run through some of the things that I've done. So with this, for instance, with this trim data set, I've done something very basic here and displayed the graph. And for most purposes, this would be sufficient, but maybe I want to export the data, or I want to add on a new function to it. It's easy to just go into another script where that function has been written, copy and paste it into this existing script and rerun it. It's probably not the most clear, coherent description of what you are trying to know, but yeah, I can expand upon it a bit further, maybe over email, or if you want to discuss it further now, just let me know, and yeah, I'll try and explain it again. Okay, yeah, so while I'm waiting for more questions to come through. So the data set I've added here is called WAPOR, and it's an ET data set. So there are different ET data sets available. This is just the one of them. And what this data set is showing is actual evapotranspiration and interception as decadal value. So for every 10 days, it's giving us the millimeter per day value. And it's the sum of soil water evaporation, canopy transpiration, evaporation from intercepted water. And each pixel represents the average ET in this 10-day period. So this specific data set here is only providing the actual evapotranspiration and interception, and there's a scaling factor of 0.1 that needs to be applied to it to get it into that millimeter per day value. So as I was saying, I've had a shapefile for an area that I've undertaken research in previously. I've already uploaded it to the script. The script is then calling on that shapefile. We add it to the layer so we can visualize it. And then now we actually go into the data set. So I'm calling the data set ET0. I'm specifying that I want to work with the image collection. I've given the name of the image collection here. Then I want to filter the data only for a particular region of interest. Fairly long period from 2002 to 2021. And I'm only selecting the ET data that I'm interested in. This function here is just for visualization purposes. It's not entirely necessary, but if you want to view the data, what I've done here is I've basically said, okay, from this image collection here, I want to map a function. So the nice thing about Earth Engine is you can apply a function to an image, for instance, clipping, or you can apply a function to the entire image collection. So instead of clipping just the one image out of the entire collection, you can map this function to clip every single image in that collection. So that's a really powerful feature. For instance, if you had to download your data set using one of the traditional platforms, you'd have to download the entire data set. Then you would open up the data set in GIS processing software such as ARC or QGIS, and then have to manually clip each one of those images just to work with your region of interest. So it's a bit inefficient that way. Within Earth Engine, you can circumvent that whole process, and you run this function, it clips the entire image. So now you're only working with ET images for your region of interest. So you've taken this massive data set and you condensed it just into a data set that you're interested in working in or working with. So this function here, this map function, is going to clip this entire image collection only for our region of interest. There's some visualization parameters. This is just to add the data in so we can actually visualize it. There's a function here to multiply the data by the scaling factor just to ensure we're working with the correct values and units. There's an additional function here where it says, okay, calculate the mean value of ET for this specific region of interest and allocate a correct date time format to that value. So how you saw in the previous example, when we expanded it and we exported it as a CSV, the date time format wasn't in a format that we'd like to use. And to prevent additional processing in Excel or R or whatever software you're using for the data analysis, we can do that in Earth Engine. So we specify it right at the outset. We apply the functions, we create this time series graph, and then we can export the data. So this is also quite a nice feature, because sometimes when we generating these graphs, if there's too much of data to work with, the system will time out and it won't generate this graph for you. So you can't use this method where you expand upon the graph and download the CSV. It'll throw up an error, but the script is still running. So in order for you to get that larger volume of data, you can write an export function. And in here we say, okay, after doing all of this processing, I want to export this image collection that I've done all the processing on. I've given it a name. I've specified a folder where it should go to. If you don't specify a folder, it will go to your Google Drive and just sit in the main drive itself. It won't go to a folder in the drive. Anything that you export over here automatically goes into your Google Drive unless you state otherwise. You can't directly export to your machine or to your external hard drive. So just be aware of that. Everything goes to the Google Drive first. You can specify a file format that you want to export the data in. So I want to export as a CSV. And then from the data that we process, we've created some additional information, but we only want the date and the ET value. So let's run it and see. Hopefully there's no errors in the script and everything works as hoped for. So again, 19 years worth of data. In a flash, it's extracted 4,697 data points or images. We see under the tasks. So remember I said that when you performing specific tasks, it will show you the task that you'd like to perform, but it won't actually perform it without you clicking run first. So if I click run here, I'm just going to take out the drive folder and hope it goes to my Google Drive directly. Alternate time series run. Okay, so it's happy with that. So you can see that task is running there. If I go back to the console, there's the ET graph for that period of time. So 4,000 values, or let's say close to 5,000 values in less than 30 seconds. There's the time series. So again, this is extremely useful because if you were to go the traditional route of downloading the data, that's going to take an eternity, firstly, just to download the data. Then you have to worry about the computational space to store the data. While you're processing the data, you need processing power, and you're going to be generating additional outputs during that whole processing procedure, and that's going to require even more space. And yeah, all of that computational effort and resources required just to generate something like this. Earth Engine has taken the hassle out of all of that there for you, and now you've only got the data that you're actually interested in working with. So let's see whether this task has run. So I'm still running, it's taking some time because it's quite a lot of data. I'm just going to open my Google Drive. So while this is running, does anyone have any questions thus far on what I just demonstrated here? Okay, so that's run. So there's this WaterNet ET node time series that we've just exported. Just download that from my Google Drive. Right, and look at that. So now the data is in a useful format. There's no additional processing required. I've got the mean value for my region of interest. I've got the date. Very easy now for me just to create a time series plot. And then obviously make it more visually appealing, which is much easier to do in Excel. Google has just basic plotting abilities, but yeah, you probably could create more visually appealing plots, but you're adding additional complexity just to do a task that you can easily do in Excel. Yeah, just to show it's the same figure. So nothing weird has happened during the export process. We're seeing the same trend, same value ranges. So yeah, quite powerful. Any questions on that? Okay. No questions on that. We can move on to the next example. If you're still typing your question in, feel free to send it through and I'll address it as soon as I see it. Let's try and find one where we've exported the image. Okay, so I'm just gonna go. Yeah, so you can use this data as a surrogate or alternate to in situ observations that are lacking. The advantage of using remote sensing is, yes, where in situ instrumentation are unavailable, at least you have an alternate data source. There will be some level of uncertainty associated with the data, but in most instances, if it's the best you have, and you've seen that it's been shown to be credible in other regions, you could use it with a certain level of confidence. Yeah, you can do this for any region. So I specified a specific region of interest when I was trying to extract this data. You could easily take that polygon and just drag it and drop it somewhere else in South Africa, and it would give you the ET data for that area of interest. You could draw your polygon anywhere in the world, run the same script, and you'll get the ET data. So that's the advantage of eventually moving over to the scripting format, is that once you've compiled the script is usable anywhere for any task. The only thing that changes thereafter, if we're using the ET example, the only thing that will change is the date range that you're interested in and the region of interest. Everything else within the script remains the same. So you can generate time series on the fly, like for all 9 provinces in South Africa, for any country. It's really, really that simple. All you have to do is just make 2 minor modifications in the script. Okay, so this one's a bit problematic. Let's see this. Okay, so this is a script that I developed to use the outputs from an energy balance ET model to help in estimating ET estimating ET using a drone image. So the spectral resolution of the sensor that we had on our drone didn't capture all the necessary bands that you can process to derive inputs to run energy balance ET model. So we had to find a unique way of how we could use that data to actually generate ET using this drone image. And that involved doing some additional processing using Landsat data, running that through an energy balance model, getting ET from there, and then finding some relationship between the coarser resolution Landsat data and the drone image. So it's a fairly complex process, which we don't necessarily need to know, but I just want to show you the output of that whole process. And yeah, this drone image is probably a couple gigabytes in size. So again, computationally intensive to process all of this data, to extract meaningful outputs from it. With Earth Engine, this whole process has just been speeded up quite substantially. I just click run. Yeah, so now we're working with data that's not housed in Earth Engine. This is the drone image, so you can see the spatial resolution quite high in comparison to some of the other data sets we are working in or working with. So it's just loading all the different outputs that have been generated. So this map here, that's, let me switch off that, switch off that. So for those of you that aren't familiar with Ndvi, it's a vegetation index, and it's used for multiple purposes, showing you vegetation density, health, and so on. It captures a lot of the vegetation characteristics. And what you can clearly see here, so areas that are in blue probably have low vegetation cover or vegetation that's in a poor condition. Your darker greens are areas where vegetation is more vibrant. So if you just look at that in relation to the RGB image, you see that we more or less capturing that correctly. Also can be a useful index to identify non-vegetated areas. So in this image, this portion here is where there's smallholder farmsteads, there's infrastructure. So yeah, just by using this index, we can clearly map those out. And this is the ET image of the area. So yeah, using the output from that energy balance model, processing it a bit further to estimate ET from the different crops and surfaces over here. So areas in dark blue is where you're having high ET rates, and that should correspond to areas where there's dense, healthy vegetation. So just for viewing purposes, we can see that seems to be the case. This region here where we can see quite dark blue. If we have to look at the drone image, zoom in a bit, we can see it's an area where there's trees, and the trees should have higher ET rates than your grassland and bare soils and so on. So if we just switch that back on, we can see that probably is the case. So as I mentioned before, everything over here is being done on the fly. And in order for us to actually take this data and create maps from it or generate time series, we have to specify that we're going to export. So there's an export function that we've added here. So in the previous example, we've exported a table, so CSV data. In this instance, because we're not working with time series, we're not going to select that option, but you could export it as an image, as a GeoTIFF image, which you could then take into ArcGIS or QGIS. So the first option is you can export the image to your drive, and it'll show up in here like in the previous example. Alternatively, if you want to develop an app for your data viewing, you need to have all of the assets that you're working with stored in your Google Earth Engine assets. And then from there, you have to give share permissions where you allow any user to access the data set without having to physically download it. So if you develop this app and this app is displaying all these different land cover maps and ET maps and so on, in order for other people to view it, you have to share that data. But by sharing the data, it only makes the data visually available, and they can't actually download the data set and use it for their own purposes. They still have to request permission from you. So that's a nice feature there. Okay, so any questions on this? Question. So we used a DJI Mavic Pro 300, I think. And it had Altum MicroSense sensor, which was integrated with the unit. It didn't come standard with the drone. It was a more advanced camera that was bought for the specific purposes of this project. So this sensor had a multispectral camera and a thermal camera. So we got data in the red, green, blue bands, near infrared, a red edge region, which is quite useful for doing any vegetation-based analysis, and yeah, the thermal band. So sensors or satellite sensors like Landsat, MODIS, Sentinel, their spectral resolution, or the amount of information they capture in the various bands, is a lot higher than what you'd get from majority of the sensors that are integrated with your drone units. But the trade-off comes now that those sensors, while they have a higher spectral resolution, their spatial resolution is fairly coarse. So for applications such as what we did in this study, even Sentinel imagery, which is 10-meter resolution, that pixel size is too coarse. You won't be able to capture the unique differences and interfield variations that the drone can capture. So yeah, there's always going to be some form of limitation, trade-off, etc. We just try to minimize that. Okay, I hope that answered your question. And the last example, again, I'll use the drone, but I'll walk you through the whole process. This is quite a popular task in Earth Engine, and it's land cover mapping. So the advantage of this is that, let's say, for instance, we have, and I'll use the drone image here again. Let me just run the script and then I'll walk you through what's exactly taking place. So while Earth Engine is hard at work, yeah, if there's any more questions, just feel free to ask. So this is quite an intensive image processing procedure. So it's going to take a little bit longer, but yeah, there's some questions. Great. Can you please request a participant to switch on? Okay, sure. Let me just mention it now so I don't forget. So if everyone can please switch on the cameras at the end of the session so we can take the group photo. Unfortunately, I got kicked out when you did this previously. Thanks. Okay, so the outputs now are starting to come up, so we can start describing this. So with the land cover mapping, what tends to happen is that you might be familiar with the land use land cover in a specific region of interest. So I'm just going to start switching these layers off and just look at this drone, the RGB. So this is a fairly small study area, but let's imagine this was at a provincial level. National level is a bit extreme. So yeah, provincial level or for a city. And we only were knowledgeable about the land cover in this part of the city. But we are required to do some form of hydrological modeling work or analysis for this entire region. With the land cover mapping, what you could do is you use known characteristics of, or you use characteristics of known land covers. So for instance, in this specific region, I know this is bare soil, I know these are buildings, I know this is agriculture. And we take the characteristics of those known land covers and then start applying them to the rest of this image to identify the different land cover types throughout this region. So just by having a limited knowledge of a small area, we can actually create a fairly detailed and accurate map of this entire region, which we can then use for different purposes. I use the example of hydrological modeling, but you can use it for identifying alien invasives, identifying areas where they need to be cleared, and so on. So from this raw drone image here, this image captures, I mentioned the 6 bands, but in this specific instance, we only worked with 5 bands. So red, green, blue, near infrared, red edge. And yeah, I added the band, or I added all of this data onto the map. So this is what we're visualizing. I've printed it just to make sure that I've added the correct drone image. So you can see in the console, there's information about the 5 bands. I've also added the coordinate information of this drone. So there was a previous question on what type of coordinate system to work with. And I mentioned that you don't have to use a specific one, Google will assign its own coordinate system onto the data set, but to see the native coordinate system that you're working in, you put in a bit of code, and then yeah, so its coordinate reference system is classified as EPSG 32736. So this is the Google Earth Engine nomenclature. You can just copy this, paste it into Google, and then it'll give you the coordinate reference system name that you're more familiar with. Additional bit of code that I've added here. So this is quite a high resolution image. The original image was 7 centimeters. And while Google does have the capacity to process this image, it does reduce the processing time. So what I did is I resampled it to a slightly coarser resolution where I get, I'll still get fairly accurate estimates, but the processing time will speed up. So the first bit of code over here is showing this was the original resolution, 0.07 meters. And after doing the resampling, I want to see what spatial resolution, make sure that it's correct. So I resampled it to a 1 meter resolution. And with the land cover mapping, there's the important part, as I said, where you take characteristics of your known land use land cover classes, and then you start applying it to regions where you don't know what the land use land cover is. And to facilitate that whole process, you collect something called training data. So within the training data, we will, you can see there's quite a bit. We'll capture information. So for, let's say, for instance, for agriculture. So if I clicked on a point here, I'm starting to collect all the characteristics, spectral characteristics of that particular land use land cover. So at the very least, if I just use the drone image as is, I can capture data for this agricultural class in the blue, red, green, near infrared, and red edge. But this might not be enough to distinguish agriculture from grassland. So there's additional features that could be associated with the agriculture that I need to sort of extract and then use these features to start distinguishing between classes. So there's several indices that you can use, which will more clearly highlight certain properties of a particular class when compared to others. So there's a variety of indices that I've derived over here for this. Some of you might be familiar with, like EVI, Ndvi. There's a green Ndvi option and so on. And this will now be collected for multiple land use land cover classes within these areas where we know what land cover is present. So after we've collected all of the data, we then provide this data to a machine learning algorithm, which will then start classifying the entire image based on the data available from those known classes. So there's several machine learning algorithms that are available. And yeah, in the past, it might have been quite complex to apply, but within Google Earth Engine, it's just a matter of calling up a name with a function. So if I scroll further down, it's quite a bit of code. It seems really overwhelming. There's several tutorials that have broken this down nicely. So all you have to do is just copy the code and paste it across. So yeah, don't get too concerned by this for now. Yeah, so back to the classifiers and machine learning. So you just call up the classifier function. You specify which classifier you want to use. There are additional parameters known as hyperparameters, which you can provide further inputs to help fine-tune the performance of your classifier. So if you run it with the default parameters, you might find that your accuracy is not what was expected. So you can fine-tune those parameters to improve, sort of like a calibration process. Alternatively, you can just switch between classifiers, and switching between classifiers is just changing the name within the code. It's not a whole complex process that you have to now process the data in a different format so you can use that specific classifier. Yeah, so once you've collected the training data, it's important that firstly you give it enough information where it can start developing an understanding of what characteristics are associated with a land cover class and then map that across the image. But also it's important to have data to compare your output against. So you want to validate the output of this classification process. Ideally, you'd like to use an independent data source for this. So you'd go out into the field and you'd collect GPS coordinates of points where there's agriculture, where there's grassland, bare soil, and so on. But yeah, most of the time it's impractical to do that, or you don't have the resources available to do it, which can be a limitation if you're, and more so if you're using satellite Earth observation data. But with the drone imagery, because it's such high resolution, you can easily collect your validation data directly off the image. So it's not as big of a problem if you don't have that independent ground truth data. So from your training data set that you collected, so you say you collected 100 points for each one of these classes, you can subdivide the training data or that training data set into a portion that you use for training your classifier and a portion that you use for validating the output of the classifier. Again, this is all a bit complex. I'm just quickly running through it. There's obviously more theory sitting behind this, but yeah, just so that you follow along. Thereafter, you run the whole classification process, and within Earth Engine itself, you can perform the accuracy assessment. So just by writing in a bit of code, you can now see how your classifier is performing. So you don't have to actually generate the output, export it to your cloud, and then take it onto your machine and do all of this performance evaluation using independent software like ArcGIS or QGIS. You can do all of this within Earth Engine. You can fine tune the whole classification process until you're happy with the output that you've generated, and then you export the final. So we can see this classification performed fairly well. We are getting 90% accuracies overall. If you expand this a bit further, you can get the accuracies of each class. So how well was agriculture mapped, how well was soils mapped, and so on. And yeah, you eventually end up with a land cover map like this. So in this land cover map, there were 5 classes that we identified for this particular region of interest within this big land cover map. And it was mapped fairly accurately. There's another nice classification procedure available where you do probability mapping using the random forest algorithm. And basically what you do here is you identify one class versus another. So using the example of agriculture, you can identify all agricultural areas versus non-agricultural areas. And this can be quite useful if you're a farmer and you want to know, okay, how are my agricultural crops doing? They spread out throughout this area. Obviously, it's physically impossible for me to go and view all of these in person, but from this image now I can see, okay, there's clearly that's where my sugarcane is, and I can see the ET rates associated with that, the vegetation health characteristics. You can do all of this with one image, and the processing required to generate all of this data to inform decision making, it can be done all in Google Earth Engine far faster than you would do it if you're following some traditional approach. So yeah, from me, that's it with regards to what I would have liked to demonstrate in terms of Earth Engine. There's obviously way more than what I've shown over here, and probably examples that are much more interesting to you. So please go through those resources. Don't be scared to engage with the coding. It does seem difficult and overwhelming at first, but yeah, once you actually get into it, it's quite enjoyable. And it can open up a whole lot of different research avenues that weren't possible before. So yeah, try and take advantage of it. It's a really powerful tool. Okay, so I'm just going to switch my video on. Okay, so before we formally end the session, Any questions? So I know someone requested the script for the trim data. I'll compile a script that you can use for trim data and for other rainfall data sets or ET data sets. Obviously, there will be some modifications required on your part. And yeah, I'll send that either to Ms. Chetty or to Mariah, and she can share it with the rest of you. Yeah, and in addition to what's been presented here, if you have any questions pertaining to your research, you'd like some advice, or you'd like to discuss things further, just let me know. Happy to assist where possible.
Sorry, sir. Can we have your email address so that we can contact you if you have any question?
Yeah, so on the title slide of the presentation, my email address is at the bottom. So feel free to email me. I'll respond as soon as possible.
So the slide has been uploaded, or it is yet to be uploaded?
I'm not sure. No, I think it still needs to be uploaded. So the presentation size exceeded the upload capacity. So I need to subdivide it and then upload it. But yeah, my email address will be on the title slide.
Oh, thank you.
Yella?
Hi.
Yes, are you waiting for me?
Just yeah, I'm waiting to see if there's any questions. If there aren't, I'm happy to close the session.
Okay.
So it doesn't seem like any more questions are coming through. So yeah, Mariah, if you'd like to close the session, I'm fine with that.
Yes, can we all turn on our cameras once again? You can stop sharing your screen.
Okay.
Others are still coming. Okay, thank you so much.
No problem. Okay, cheers everyone. I hope that you'll engage with Google Ad Engine in the near future.